Today we're going to talk about developing a quantitative measure to avoid signal aliasing. Specifically, we want to figure out to avoid signal aliasing, i.e. when our sampled signal takes on a different signal than the original signal of interest, what is our condition on f of s? So how do we pick a sampling frequency such that we could avoid our signal aliasing? So let's go ahead and look at this sine signal. So what is the frequency of this signal? Well, I know the frequency is omega, but here omega is going to be in units of, or this is our frequency here. So omega equals pi, but again, we want to write everything in terms of cyclical frequency, so omega equals 2 pi f. So if omega equals pi, frequency is equal to 1/2 hertz. So that's what we're dealing with in terms of our signal. So this is the maximum frequency of our signal. There's only one frequency, essentially in this signal, and it's 1/2 hertz. So that is my frequency of the signal that we're trying to deduce here. So this is just kind of showing it here. So this is the frequency, and it's the maximum frequency of our signal. So let's see what happens if I sample this signal. So this is my y of t here. So this is my original signal y of t. So let's see what happens if I sample at an f of s is equal to 0.5 hertz. So this is basically equal s equals 1/2, and I know that f sub s is equal to 1 over delta t. So I know that my delta t here is equal to 2 seconds, and you can see that right here. So this is the signal that I'm measuring. What is the apparent? So when you have a signal, we talk or when you sample. So this is our sampled signal. So in our sampled signal, we're going to ask or kind of see what is the apparent frequency of this signal. So what is the apparent frequency of the signal that we have just sampled? So this is our original signal, that blue curve. We're going to sample based on these points, and based on our sampled signal here, what is the apparent frequency of our sampled signal? Well, that apparent signal, that apparent frequency is 0. So it has an apparent frequency of 0 hertz. So this is not correct. So we have an apparent frequency of 0 hertz. So again, we have indeed aliased our signal. So we cannot sample. So again, our original signal of interest, it has a frequency of 0.5 hertz. Here we can clearly see that this signal here, right here, if my f sub s is equal to my f of the signal, specifically the maximum frequency of my signal, then I'm going to get aliased. So I cannot sample at the maximum frequency of our signal. So I need to sample faster. I need my f sub s to be greater than f max to avoid the signal aliasing. So that's kind of the key. So that is making sure. So at this point, we have to make sure that at least we're greater than the frequency of our signal. So what if I do my f sub s is equal to 75, so 3/4, so 0.75 hertz. So again, my f of my signal was equal to 1/2. So now our f sub s is greater than the frequency of our signal max. So let's see what happens. Well, let's look below. So this is my original signal again. So my signal looks like this. It goes down, up, down, and down again. So what is the apparent frequency of my signal? What's my period? Well, my period, I go from here, down, up, down, and then I go down again, and it would go up again, etc., etc., etc. So I go here, 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 and I'm going here, here again. So my period is from here to here. So my period t equals 4 seconds. So I know that my f apparent equals 1/4, which is equal to 0.25 hertz. That is not, again, I have aliased my signal once again. My frequency of my signal is equal to 1/2 hertz. So again, I've aliased, so I can't just be greater than, so my condition here previously, that my sampling f sub s has to be greater than f signal max, that doesn't work either. I have to be even large. I mean, again, this doesn't work, but I need to be even larger. So it didn't work this time. So just going to 0.75 hertz did not work. So let's go back up to this page again. And here, still not sampled correctly. Still have our parent frequency of 0.25. So not frequency of our signal. Faster, faster, faster. We have to sample faster. So what about when I do f sub s equals twice my f signal max? Let's look at what happens here. So again, that means that my f sub s is going to equal 1 hertz. Well, let's look at our signal. So at 1 hertz, nope, this doesn't work either. Now you'll notice if you phase shift this, and this is kind of the danger of if you phase shift this by 90 degrees, we will actually sample correctly. So you can imagine if I phase shift by 90 degrees, it'll be here. Oh, excuse me. The sample would be here, 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 and then I would be sampling this correctly. I would get my correct frequency. But again, this is kind of the danger of sines and cosines. So at this magic number, sometimes you can get away with f equals to f of our signal apparent. So sometimes you could get away with this and not signal alias, but because of this 9 degrees phase shift, we cannot use this condition either. And this is a perfect example. If you phase shift by 90 degrees, I can go from sampling properly, getting the correct apparent frequency, to getting 0. Just by that, again, this sine pi t plus some delta. So that's what you could kind of encounter, and then everything gets messed up. So we cannot use this condition. We will still get aliasing, and that is observed by this kind of apparent frequency of 0 hertz in this graph right here. So what is going to work? Nothing is working for us so far. So 2 doesn't work, twice doesn't work. Keep getting these apparent frequencies. Can we ever properly sample our signal? Well, let's see what happens when we do. We sample at twice the maximum frequency of our signal. So when we do that, we will not have signal aliasing, which we can see right below here. So now, if I look at, okay, here, now my period t equals 2 seconds, excuse me, 2 seconds, and now my frequency of my apparent equals a half. So I have properly sampled my signal, and then my apparent frequency is 0.5 hertz. So the key thing here, to avoid signal aliasing, I need to make sure my sampling frequency, f sub s, is greater than twice the frequency of my signal, specifically the maximum frequency. Now, why do I keep saying the maximum frequency? Well, we've been looking at this function, sine of pi t. But you could have a function where it's y equals cosine of pi t. I could do sine of 100 pi t. You will have this in some examples coming up. Cosine of 0.5 pi t, etc., etc., etc. So we need to make sure that we are greater than the maximum. The sampling frequency has to be greater than twice the maximum frequency of our signal in order to properly, again, in order to properly capture all the high frequency and low frequency basically signals in our signal. Anyways, so that is our key condition here. So if we cannot meet this condition, our signal is going to be aliased, our apparent frequency is going to be different from our signal of interest, and we cannot trust those results moving forward. So that is kind of the key thing. We don't know what, where we could be aliasing. So unless we build in some high frequency, high pass filters, you cannot trust that signal. So next time, this is a really, really kind of key point. So keep this in mind when you're designing an apparatus and you're making measurements in basically whenever you're doing Fourier transforms. So next time we're going to get into how do we transform our continuous Fourier transform notation into discrete Fourier transform notation. So we'll talk about that next time. Thanks. Have a good one. I'll see you in the next video. Bye.